Before we begin this chapter, let me tell you about the status of chapter 13, because chapter 13 is not finished, and in fact there are difficulties in finishing it right now. I have started to write down some proofs that I don't yet know how to finish. And well, but I would like to finish them in some way, so maybe I can finish them pretty soon. But also most of the chapter is not yet written. So there is a beginning which is written, and then there is some pretty rough material, and then some proofs that are finished, and then there's some proofs that are not finished. So I don't know what you would like to do with chapter 13 next time. On the other hand, chapter 14 is finished. It's a very long chapter. And
it's an interesting one about the monad transformers.
Yes. Well, the free type class chapter is, in my view, is also quite interesting, but it's just that I discovered a lot of things that I didn't know how to prove, questions that I didn't know how to answer, and it took much longer than I thought to figure out. And yeah, so
the things that you haven't proven, you're pretty sure are true, right?
Well, they're true, except until you prove them, you don't know.
Okay.
So, it's just that I may need. So I spent a very long time trying to prove a certain thing, and then I realized that I don't have enough assumptions. I wouldn't be able to prove it. So I need more assumptions. So this kind of thing could be the reason that I'm not able to prove it. So I'm trying to prove something that actually is only true with more assumptions, and these assumptions might be at hand or might. So one I just discovered two weeks ago, that I really need some complicated technical assumption that requires me to rewrite other definitions. And anyway, so this is kind of what I wanted to say. So we can do, certainly I can just we can still have a meetup on that chapter, chapter 13, to read whatever is in there, and I can then, if I have time, I can explain what else will be there.
Right, that would be the sort of thing where we would definitely want to have you available as a guide.
Right, yeah. Well, I'll try to organize next time as well that I'm available.
Right, so, I'm not sure we will get to 13 next time. 12 seems long enough.
May not.
It might take.
I mean, I just wanted to say that I certainly thought I would have enough time to finish it last year, but then I discovered that I actually don't understand things so well, and I'm trying to prove things that aren't true, and so on. So this is exciting, but this has been the same with every chapter. So in every chapter, I discovered that I don't actually know certain things, and that certain things that I thought that I know how to prove, I don't know how to prove. So sometimes I had to drop things, and sometimes I had to come up with a proof. All right, so that's
actually before. Do you mind if I ask a question? It might be a little bit dumb question, but I'm curious about your thought process. And you mentioned that when you say you try to prove something and then you got stuck, how do you know that you're going in the wrong direction? And then what are the things that you look for? Is it something that you just haven't figured out yet? Or is it something that you know you're going in the wrong direction, you have to back up? I guess it might be a bit general, but I'm just curious.
Well, yeah, well, specifically, I was trying to prove that certain type classes satisfy certain laws. Now the laws are equations, so I'm writing this equation and I'm trying to prove it. And then I see that there is some combination of functions that should be equal to another combination of functions, and then I can prove it. So, like, you know, in the monad laws, for example, the composition of pure and flat map is an identity. Now I have a composition of pure and then something something and then flat map, but not pure and flat map together.
Hmm.
Now can I move them together so that then I can use this law and then I'm done. So I spent a very long time trying to do that, but I could not. I could not find any other laws that I could use in this case. So essentially, this was the wrong direction to go. And then I realized that actually I might need to assume that something else holds so that I could move pure and flat map together. And this might not be actually automatic. And unless I assume that, then things don't actually work out. And so, but let me explain what this is about. So my thought process is that if I cannot find a proof reasonably quickly, and there doesn't seem to be any way to proceed, it might be that I'm just assuming things that are not true, and then I can try to find an example when they're not true. Just as an example, free type class, or let's say free functor or free monoid or something like that, is usually defined in category theory through some adjoint functors, free forgetful adjunction, or some complicated stuff like that. And the result of that definition is that the free, you can construct sometimes this free, say free monoid you can construct. It will automatically satisfy the laws of a monoid because you are constructing it kind of by definition. But actually, when programmers write code for those things, sometimes programmers write code that does not satisfy all the laws. And yet that is not a problem. So I am trying to find weaker conditions than what category theory assumes, and define free type classes not through the free forgetful adjunction, which in my view, in any case, it's too heavy, it's too complicated. For programmers, it is not intuitive, and also it does not give you a concrete recipe for doing it. And so I'm trying to find weaker assumptions. And so in this situation, I don't know what assumptions are correct. I'm willing to take more assumptions when necessary. And so I'm trying to prove the law. I try to see if I can construct the proof. And at some point, I see that I cannot exchange some functions. And until I assume something else. So then the question is, what is the smallest thing that I need to assume to make that work? A very similar thing happens in the monad transformer chapter, where I need to assume certain things for monads to be able to compose. What are those assumptions? Well, we write the laws. We cannot prove that the composition of two monads is a monad until we assume something. So what is it that we assume? Well, we assume that which allows us to proceed with the proof. So that is my thought process. I hope that answered your question.
It's sort of, I think it's very interesting to be able to observe your thought process, and thanks for sharing. Yeah. And then so I feel that it's probably you're more experienced and you probably still have a gut feeling when you encounter the situation and then the assumptions. I don't know. I mean, what to take as an assumption and then that kind of thing is something probably
you have to do quite a lot of work to figure this out. You assume one thing, then actually you can assume easier thing maybe and derive that and so on. but eventually maybe you actually have to assume more. Like for example, right now it looks like my type classes all have to be traversable.
Mhm.
Is that enough? Maybe. I mean, I'm not sure right now, but that's what it looks like that I need to prove that they're all well, this is, for example, monoid has just two methods, the empty element and the composition. And all the laws involve just a finite number of values. So it means that when you describe those things through functors, you have functors that contain a finite number of values. And traversable functors are those that contain a finite number of values, or maybe countably infinite number. Well, finite, but not bounded, right? So because you can traverse them, you can iterate over them in some order. So is that what I need to assume about my type class? That all the operations only involve a finite number of values? Maybe, because that's kind of, we don't have examples of operations that involves an infinite number of values at once. So maybe that's okay to assume that. Anyway, so actually I might have to assume that. Right now I was hoping that I don't have to, but I am at the point where I'm staring at an equation that should hold for all x, but it only holds for the x that you can obtain by mapping from integers to x, which means that your type must contain only a finite number of values. So anyway, I don't want to dwell on this, but you do have to go through a lot of calculation and try to find the proof. And if you can't find the proof, maybe this is because you don't have enough assumptions.
Are you saying that all monoids, the set, the carrier is finite?
No, I'm talking about the operations of monoids, because you want
just the two of them. Okay.
There are two operations, and they involve
a
finite number of values. So, because you want to construct a functor that describes the operations. You don't need the monoid to be finite. You want the functor that describes the operations of the monoid, and that functor must contain all the arguments of all the operations. So it must be some collection, some kind of polynomial data type that contains a few values that are arguments of the operations. And so that is what needs to be finite.
Okay.
So, but if you look at traversable, so the main message about traversable functors is that all of them must be polynomial. So you cannot have a traversable functor that has inside it a function type, because you cannot enumerate all values. If you have functions from some unknown type, you cannot enumerate all those. Like if you have a function from integers to something, you cannot enumerate all the values because there are infinitely many integers. Neither can you enumerate all functions. So you cannot traverse this. You cannot traversable. So the easy way of thinking about traversable is that you must be able to extract all values into a list, and you must be able to put them back. So it's a data structure where there is some order on the elements, and you can extract them one by one into a list. And then you can somehow collect enough information so that you can put them back into the same places after making transformations, of course, on them. So
I thought somewhere you were sort of saying that traversable doesn't generally allow you to keep position information. It's sort of like you don't know where the thing is.
well, well, I have a discussion in this chapter about this, where and the main thing is that there are methods that are fold and the methods that are traverse. So the fold discards the positioning information. It traverses your structure, it accumulates something, and then at the end you have a value. But you don't know anymore how to restore.
Put it back. Yeah.
How to put it back. So you, for example, you could accumulate through fold, you could accumulate a list of all values contained in your data structure in the traverse order. But that's it. So you have a list. You don't know how to put them back. You don't know how to
That's what I was wondering. Yeah.
Yeah. But that's fold. So foldable. Sometimes people make a type class foldable and separate from traversable. I don't do that because all foldables are also traversable and vice versa. There is no difference. So there is just a difference of what functionality you want. So if you don't need to be able to restore data structure, then you don't need to traverse. You can just fold. And fold is equivalent to just transforming your data structure into a list. And a lot of so you see, so there's a lot of cases where you don't care about restoring the structure. Imagine that you had an algebraic data type, polynomial data type, where you had different disjunction parts that carry different kind of information. Like you have 1 plus a plus a plus a times a plus a times a plus something else. So you have different disjunction parts that carry different meaning in your program, but they contain the same number of elements, right? So if you extract that into list, you will lose the information of where they were in the initial data structure. So in certain applications, you don't need to keep that information. It's sufficient to just extract all the data in the correct order and perform some aggregation and do something. But in other applications, it's not enough to do that. So the typical task for which it is not enough is when you want to do the operation of zip with index. So right, so in Scala there is this operation, zip with index, and right. So let's see. Whiteboard. Zip with index, and it's a so typically it takes some type parameter a, and then it goes from some collection of a into a collection of pair of a and int. So, right, so this is the typical zip with index. So in other words, you iterate through your collection and you don't change any values in there, but you put a label, the index on each of them. And so if you can do that, it means that you have extracted the data, you counted it, and you put it back into the right place with the counter value attached. So you don't only traverse, when you traverse, you don't only enumerate all elements and collect them somewhere, but you are able to put them back into exactly the same type structure as before, into the right places with no, and then there are laws of this. So this this operation zip with index is impossible unless you have traverse. Because you need to.
Sorry, a question about that.
Mhm.
Could you explain a little bit about the difference between lists and collections? Because I don't know the difference. Sorry about that, but what's the difference between what's the type the as a type why a collection is what is a collection?
It is a traversable functor. Any traversable functor. I'm just using a general idea that this is some kind of collection, a tree maybe, or some other thing.
All right. Thank you.
You know, list of trees or whatever. I don't know what that data structure is. A tree of lists, or I don't know. So I'm just saying that if you want this functionality, for example, zip with index, then you need traversable. So you need the traverse method. And the traverse method has a difficult type signature. It has two type parameters. And it gets from actually it has another type parameter, which is some functor f, and it must be applicative. And then from A to f of b, and then from collection A to f of collection B. So this is a kind of this is a difficult type signature to understand because it contains an arbitrary applicative functor f. So it must work in the same way for all applicative functors f. Traversing the collection and then somehow collecting all the effects of f together as you traverse. And then you have to put all of the values back because see, these values here, these values of type B, you're supposed to put them back into the collection at exactly the right places. So you're supposed to be able to extract this B somehow and put it back in the same way, in the same shape. So this is quite a difficult type signature, actually, which is actually also, well, it is equivalent to type signature, which is called sequence, which is collection of f of A going to f of collection A. And this means you have a collection of effects with values inside them, and you can iterate over all those effects, concatenate them together using the applicative, and have a one big effect as a result. And then you can get the values back. The values of A you can extract back into the same shape as before. And this must satisfy certain laws, but essentially the shape of the collection must not change when you do this. So, for example, if this is a tree, you're not allowed to rebalance the tree when you do this. So you're supposed to,
I was kind of wondering, looking at traverse before, whether you could just, map that A to F of B function, like if your collection is list, could you just map that function across the list and then collect the pieces? Well, this is exactly, I guess, what sequence does.
Yes, that's right. Yes.
So, okay, that's cool.
They are equivalent, but you need identity.
Oh, okay. And I guess my other question is, when you say effect, what is that?
Any type constructor into which you wrap.
But so is the effect?
I'm using it in a very straightforward manner. It is just any type constructor that wraps your result values. So you have some kind of computation and you want to compute result values of a certain type and like of type A. Right, so here you have a collection of type A, collection of values of type A. So your type A is the interesting value that you want to get at the end of your program. And but here you have f of A. So this f is some kind of type constructor that wraps your result. And
So
you have to extract it somehow from that before you can use your program. So that's effect just means a type constructor that's wrapping your result, and you want eventually to get rid of the wrapper somehow. And the examples are option and list and future.
Yeah, that is the terminology effect is used with monads, right?
Yes.
Even though it's not necessarily side effect.
No,
but
there's nothing. There is no side effect.
But people use the word effect to distinguish between, let's say, an expression like A plus B as an object, as opposed to the result of evaluating A plus B with specific A and B, to distinguish the algebra representation versus the end result. And that's how monads are used in general, right? Like, so that's why I think the word effect is used there to represent things that are not necessarily in final form, but we want to think of the things in their intermediate form, like the syntax of something. So in an algebraic expression as opposed to the result of evaluation.
Right. Although the expression is one example of an effect.
Yes.
It's a specific kind of wrapping and a specific kind of evaluation that you need to do to get the result out of it. And for example, for the Scala future type, then the wrapper is this future constructor that represents a running process on a thread. And then there are specific APIs to get results out of it. And
right,
for
which is what I'm calling the normalization or evaluating.
Evaluation, yeah. And in my book, this is called running.
Right.
Running the effects. So if you have for example, if you have a list, then it represents a collection of values instead of a single value. So somehow running a list means you need to choose which one you are using as a final result. Right. So you can imagine this is application specific, what you use as an effect. And the interesting thing about traverse is that it is parameterized by an arbitrary applicative effect. So not just an arbitrary type constructor F, but a type constructor that allows you to merge the effects sequentially, one after another. Right. So we just had the applicative chapter. So the applicative, right? So
that's
the applicative.
That's where you have the notion of the monad, right? I mean, monoid, that you need to be able to have a combining binary operator.
Right. So you can have an operation like this where you have two values with effects, maybe two different effects, but of the same type F. And then you merge them somehow together into a single value of the product type and a single effect wrapping it. So, for example, if you have two futures, and this means you're waiting for both of them to be ready. And that is the effect here. And if you have two lists, then you have a zip operation on lists. And if you have other, like two trees, then you have a zip operation on trees, and so on and so on. So for each effect, there will be a different way of merging those effects. But traverse relies on this merging, that you have an empty effect, and you have a way of merging two effects. So you traverse in your collection. If the collection is empty, then you know what an empty effect is. And if the collection is not empty, then you have some effects in it here. Then you merge those effects into one big effect outside. And then you put the values, you evaluate the effect, but in such a way that inside this F, so that the results are put into the collection back. I actually, maybe someone wants to share the book. I don't know, because I talk about this a little bit in the book, how to understand the difference between fold and traverse, and how to implement traverse. Because to implement traverse, you have to keep track of the location in your data structure. So you're gathering. Like I have examples of tree traversals, and so in order to do tree traversals, you need to keep the information about where in the tree you are, so that you can put labels back in the right order. Which you don't have to do when you're just folding. You don't need this information. So that is my intuition about what traverse is doing. But it turns out that all data types that are foldable are also traversable, in at least, and vice versa. So if you have traverse, you can derive fold. If you have fold, you cannot derive traverse. But
You cannot.
No.
Okay.
Because fold is the same as converting to list. This is not obvious, but this is actually, I prove this as equivalence between types of functions. There are different equivalent formulations of fold, and one of them is fold map, and another is monoidal reduce. For example, you have a collection, let me write down, collection of a monoid M to M. So if you can implement this function, just one function like this, for any monoid M,
Then it's foldable.
yeah.
Yeah,
That
that's
is-
the reduce, basically, right?
That's right, that's reduced.
Yeah.
So the
Simple.
reduce function. If you can implement that function parameterized by monoid and natural in the monoid, then it's a foldable. You can derive fold from it, and vice versa. And I actually proved the equivalence, which is in that chapter. So yeah. So but when you do this, when you reduce, you lose all the positioning information. You just know that you concatenate them in the right order. The traversal order was right, but that's all you know. So if you have a tree, there might be different traversal orders in the tree, and or even in the list, there might be different traversal orders in the list. You can traverse in one direction or in the opposite direction. And so the reduce function guarantees that you are going in the traversal order, but that's all. So it doesn't know what that order was after you have computed the value. So you have computed your final value, and that's all you have. Anyway, Can I ask someone please to share the book, because I don't have right now.
Yeah,
Anyway.
I'll do it. I'll do it in just a minute. But I had a
Okay,
question
sure. Yeah.
about what you wrote first.
Yeah.
I was just trying to wrap my head a little bit about the intuition. And so if F here was like option,
Yeah.
then it doesn't necessarily give you back the value, because if there's a none anywhere in there, then it would just like be, or nothing, whatever. Then it would just, the whole thing would be nothing, right?
Yeah. I guess that's right. Because option is such that once some place is none,
then the whole thing's none.
Then the whole thing is none. So
right.
Yeah.
So when we say effect, in that case, it's sort of it's not something that's sort of added onto the data. It's sort of it's wrapped around the data. That's kind of what you were saying.
Yeah, but
the function sort of wrapping around it.
Yeah, I mean, this function that I just wrote is an example, right? This functionality. Now, you might not want to implement it in this way, that, you know, if even one option here is empty, then everything is empty. But in some applications, you might want that functionality. But usually, most often, what you want is that you want to get rid of the empty options, but keep all the non-empty ones. And yeah, well, that's not traverse. So that's a different function.
That's not traverse. Okay.
No, that's a different function. Because that does not, because for option, see, you have to implement this for option. There's no way to keep any information if one of those is empty. So, and traverse must work in the same way for every applicative function. So it cannot have an exception for option and use something else just because it wants to. So in any case, now with option, that's a filterable. If you want this kind of transformation that deletes certain values out of your collection, that's filterable. That's what you want. And filterable actually is equivalent to this function.
Okay.
Where you just whenever you need to, you delete all the empty options and then you keep only non-empty ones. So if you can have that function, then it's a filterable. Traversable is not about that functionality. It's not about deleting some elements and keeping some other elements. Traversable does not delete any elements. It's supposed to keep all elements. So if you cannot keep all elements, then you have to return empty.
So if F was list, then you'd end up, you'd start with a list of A, and you'd end up with a list of A. But is it the identity, or is it kind of what?
You mean if both of them are list, if the collection is list and F is also list. Right. Yeah.
What does traverse do?
That's a good question. I will add the exercise to the book.
I think this is where the specific nature of the function comes into play, right? And this is going to happen later on when you talk about how do you distinguish between, you know, some morphism that just maps to the empty list all the time and versus something that actually produce something. And I wanted to, when we get there, I was going to say there needs to be an ordering, I think, of functions, or that so that something has more information versus less. And therefore, when you pick an arrow that satisfies this particular type, you want to pick the function that's the biggest in some sense, right? Otherwise, you can trivially come up with a list, the result function that just maps everything to the identity or something like that, and you lose out all the information. But it's less informative than something that actually does something more. Like, so I think I was going to mention that later on, but in this case too, you're losing information by extracting by switching the option outside of list, right?
Yes.
So list in a sense is structurally conserves information, but
Yeah.
option does not.
No.
When you switch things, you lose that. So and computation really is about losing information, right? You're discarding information as you evaluate things. Like 1 + 2 has more information than 3, even though 1 + 2 evaluates to 3. So each time you're losing information, but that's the nature of computation. So that's the reason why we have this, and you can't go backwards, right? So
yeah, not backwards.
Yeah.
No.
Yeah.
Very interesting point. Thanks.
Right. It's like having unreversible computations or type, or so, right.
Did you know that thermodynamically, if you can have a computation that reverses,
Right.
then you can use
Right.
almost zero energy. But if you have computation that's not
Right. But not
reversible, then heat has to be generated that represents the information loss, right?
right. So you can get heat from type transformations, right? Right. It
That's
was
why
called the
that's why
I don't
CPUs
remember.
get hot. The more computation you're doing,
Right.
the more information you're reducing, right? At the end, you have one number. At the beginning, you have like million numbers. And so all
Yeah.
that information has to go away in terms of heat.
Really? Okay.
Whereas if you had a reversible computation, then theoretically you could use very, very, in the limit, no energy to go back and forth. But the problem there, of course, is
Right.
you don't have any insight, right? If you do a reversible computation, then the result of that computation is going to have the same amount of information as before, and you don't know what is relevant.
Yeah. You did not actually
Right. But
take the
what
parts that is relevant yet. And you
Yeah.
did not erase. You did not
the
erase
interesting
from
point,
memory. Go on.
right. But the interesting point here is that this effect is studied most of time from the point of view of logic gates and these kind of things, showing that which kind of gates are reversible and not. But here we are saying that this fact from the from the functional programming point of view, right? So it's quite interesting. Right.
Right.
Should I share the book?
Please.
That do it?
Yeah.
Yeah. I guess I'm not quite at the beginning. Okay.
I thought you're changing the type signature and putting the sequence at the end makes a lot more sense. So that you
Oh.
can then compose things. And here's an interesting comment. Clojure, the language that I develop in, the inventor of it, introduced the notion of a transducer. And basically, a transducer is the reduce function without the sequence at the end, right? And so you abstract the sequence, the data that you're actually applying, but you just have the algorithm of what a reduce does. And by doing it that way, you can now compose all these things, right, in a high level way that reduces the need for generating intermediate values, etc. So that's kind of interesting.
Right, that's very, Haskell functions generally have if they operate on some sort of collection, they have it as last argument for the same reason.
Right, exactly. And so you've got the fold left defined as the composition of the, update x1 and update x2, etc. Right? So, yeah.
I'm not sure what you're saying there, because fold left, the sequence isn't at the end, right? But were you saying, I'm not sure what you were saying.
Okay, maybe in this example, the sequence is already split and put into the update. Okay. All right. Maybe this is not the place that I
I
was
mean, you
looking
could
at.
probably write fold left in the other order. You could have the B0 and update first, and then the sequence at the end.
Mm-hmm.
So what would
Right.
that bring us exactly? Because we're not going to compose different fold left because the result is not a sequence. So when you do a transducer, the result is a sequence. Then it makes sense. You have a transformation from one sequence to another. That's actually scan function. Which,
Right.
Right. So that makes sense then. But in Scala, that is done by the syntax where the first argument is to the left of the function. So you say x dot transform dot transform dot transform, which is more or less the same as composing the transformations. But
right.
but yeah, so I will think about it. It's a good observation. Maybe I will just change the type signatures here so that the sequence is at the end. Maybe it will help me in the future. I don't know. What I mean is that the proofs might be shorter or more clear. I'm not sure, but yeah, I'll think about it.
By the way, I think in chapter 2, you don't call it fold left, you call it left fold.
Oh, I'll have to think about it. I don't remember now.
I guess
Left
I can
fold.
get back here. This is
Fold left. I call it fold left.
It's in here somewhere.
Okay. Well, I have a function called left fold. Maybe
Yeah, left fold.
temporarily.
Okay.
Then I have a standard function that is fold left.
Fold left. Okay.
I mean, this is left fold is just kind of explanation. Maybe
Okay.
Then later I say this is called.
Okay.
This is fold left in the standard library.
Okay. Well, yeah. Just when I went back to chapter 2, it's like, wait, where's fold left? And it's like, oh, it's left fold. But I see. Later on, you switch it around again. Okay. Yeah. And then you sort of say you can visualize fold left by, if you switch around this update function, then it takes each value A and leaves a B to B function, and then you're just sort of composing them like one after the other. So that's kind of cool.
Yeah, I mean in some functional programming books, they say that fold left is just to take the list and you write it out in terms of constant nil, and then you replace cons by update and nil by b0, and then you get the result. That's what fold does.
Or a recursive definition, right?
Yeah, well, this is, non-recursive definition is useful for intuition.
Right.
So you just, a list is a sequence of some constant operations. So you just replace all of them through different operations and you get a different value. That's what fold does. And actually, the church encoding of lists makes it explicit. The church encoding of lists is a higher order function, which is a function of updater and initial value. And so it's kind of explicitly saying, I'm a fold. I'm just a fold waiting to be applied to something. Give me the functions that you want me to fold with, and I'll give you the result. That's what the church encoding of lists does. But later in the next chapter, I'll talk about church encoding of lists. I actually don't know if I explained enough about that. I will have to write quite a lot of explanation about that. I do have proofs of church encoding, but that's because they're non-trivial, and I wrote them down first. But anyway, so yeah, so fold map is the function that is kind of more general, and now it has the type signature you want. The sequence is at the end.
Yep.
So just one observation about this. I always like, there's fold left and fold right, and it's like, well, which way do they go? And here, I mean, I think it's generally called fold left because if you were to do this the functional way, then B0 would be at the end, and then update of X1 would be to the left of it, so you're sort of computing from the right end towards the left, right? I think that's correct, right? But this notation kind of switches it around because it looks more like you're going to the right. But
now that you mention it, maybe the word left needs to be explained by putting an extra pair of parentheses in the binary operation, the plus circle, and put parentheses around update X1 and update X2, an extra pair of parentheses there. That would make it clear that we're doing left association first, right? As opposed to fold right, which is the right association first. Don't you think? Otherwise, why is it fold left? What's significant about left?
Well, first of all, the monoidal operation is associative, so it doesn't matter where you put parentheses in there.
Then it should just be called fold.
No, because you see, there's a traversal order here. X1 goes before X2. And that's important because the monoid doesn't have to be commutative. So
I see. So
the traversal order is left to right. The traversal order of the collection is left to right. So you begin with the leftmost element of the list, and you start with that. That's the first computation you do. And then you get the result, and you put that result into the second computation. So B0 is inserted into the updater with X1. And the result of that is inserted into updater of X2. And the result of that is inserted into updater of X3. So the traversal order is left to right. And there is a traversal order here. It's not just it's not just arbitrary. Now you could do any other traversal order. And that would be a different, not equivalent implementation of fold left. Which for some, like for example, you could say, I always begin with the second element of the list, go to the end, and then I take the first element. Why not?
So Fold right just would work the other way. You start
Yeah.
at the right end of the list.
Yes, yes. You start
and
with
work to the
extreme.
left. Okay.
Start with extreme.
Boy, what is usually called fold right is associated differently. But
Yeah, because
for an associative operation, it would give the same result because the arguments are actually in the same order as the fold left. It's not reversed. It's not a reversed list. It's just a list where the operations are associated differently.
Yeah, that's my intuition too. That's why I was thinking putting extra parens there, but because it's associative, it doesn't matter. But is that always the case? Do we only use associative operation when we do a fold?
well, when you do a fold, you do an operation of type A to B to B, right? So
Okay.
B to B is a monoid. Monoids are associative. Now, something else is going on here. If you want to change the order, you can change the order. And what is fold right exactly? It is, I'm not sure what, I don't remember now. I think it's evaluating, it's evaluating putting functions on the stack or something like this.
Well, a fold left
I don't remember
will,
what that is.
a fold left on a list will do the operation on the first two elements and take that result and do the operation with the third element.
Okay.
Whereas a fold right will first do the operation on the tail recursively and then do the then uses the tail result as the right operand for the operation with the head.
Mm-hmm.
Right.
Okay.
But if the operation is associative,
It
then
doesn't make any difference.
it doesn't make any
Yes.
difference, right?
That's right. That's right. Yes.
So
However,
usually we apply right and left differently because we are using non-associative operations then?
Right. That would be
Yeah.
where you
Okay.
would get a difference.
Okay.
where is that operation here in this type
Yeah.
signature? I don't see. You see, there's a
Okay.
reduce. There's a reduce, which is reduce left and reduce right. Now with reduce, the type signature is not A to B to B. There's only one type, right? So you have a binary operation. So you have A to A to A, and then it's no longer equivalent to this. So then there is a difference because it's now A to A to A. But with this formulation, you have two different types. So then you begin with a different value, B0, which is of different type, and then you accumulate with X1. And that is always going to be an associative way of doing things. So if you want to reproduce what happens with reduce left and right, then you would have to write different updater functions, essentially. You would have an updater function that performs a different computation. So I think that's the solution of this conundrum here. Reduce right would be expressed through fold left using a different updater function. The updater function with switched arguments. And so fold left, as formulated here, doesn't have any difference between left and right. Maybe I should not even call it fold left because it's confusing.
Yeah,
Well,
I think
pretty
so.
standard though.
It's pretty standard, but you know, it's confusing.
Yeah, it's confusing. But I mean, if you had a fold right, is it that the B0 ends up being used at the right end?
No, I think that's the same.
No.
I mean, the only difference between
No,
fold left and fold right is the association of which of the binary operations are done first. But because they're associative in this case, it doesn't matter. But in practice, you know that you're doing the left, the MF plus the left one before the right one. That's left, fold left. and vice versa, right?
Yeah.
So, yeah, okay.
I think there's a difference with respect to laziness,
Yes, it might be.
and you
Well,
can use infinite. You must not have a finite list to operate on or to traverse.
no, it must be no. Traverse can only work on finite structures. So you cannot use infinite lists for traverse.
I was going to ask about that because Haskell and Clojure have lazy generation of, like, ranges that can go from 1, 2, 3, etc., unlimited, right?
Yeah.
And as long
Yeah.
as your functions are dealing with only the prefix of that list, right?
Mhm.
Then it's well defined. So
Yes.
potentially it could not terminate, but you always take a finite section of it, and then it's meaningful. But intermediately, you can think of it as unlimited. So I'm wondering, in this case too, for example, if the list was infinite, but then left of it you said take 10, right?
Yeah.
Then the semantics for fold left could be defined on an infinite structure. Traverse could be defined on an infinite structure, I think, right? So
No. No.
no,
It's just that
okay,
no, because a fold is supposed to terminate, and fold is supposed to perform these computations. Now, if you say that,
I
okay,
see,
well,
fold. Okay,
in some cases, what you're saying is that suppose this update function. So I'm looking at the equation at the top of the page 470, just in the middle of the screen, right? The top of fold map of
Mhm.
updates
This one?
is update of x1, update of x2, update of x3. Now,
Mhm.
suppose that this operation plus m were sometimes lazy, and sometimes it gives you it does not need to compute the right sometimes, but
Right,
it cannot always be like this. But sometimes it doesn't compute it. Then this thing would sometimes terminate even with infinite lists, but not always. And
right,
fold map is not supposed to know what update does and what the monoid does. The fold map is supposed to be general for any monoid and for any updater function.
right.
And
Okay,
so we cannot put that logic in the fold map. We cannot expect that the monoid operation will sometimes be lazy and so on. Sometimes we'll discard arguments without evaluating. We don't know that. And so
yeah, I think you're right about fold. Maybe I'm
yeah.
thinking of traverse then.
Well, then that's a question, right? Because
Yeah,
traverse is supposed to give you a data structure which is wrapped in some effect. Now, this effect could involve laziness
yeah.
in some way, but I don't know. So actually, I don't have any examples of how to implement. On the other hand, I do not actually treat laziness in my book very
Right.
much. So I'm not very well versed into the details of laziness. Like, for example, can you actually implement traverse of an infinite list in some way? My answer would be no, but so my intuition is that traverse needs to iterate over the collection, going through every element once and accumulating the effects. Now, you cannot do
It
this with an
seems,
infinite collection.
I mean, it seems like you could do the laziness by sort of generating a stream, right? Where
Won't be traversable.
I think this is where
Hmm.
we have to distinguish between actual programs that terminate versus the mathematical definition. My intuition is that traverse could be defined on infinite list mathematically, right? There's no problem with that. But obviously in practice, you want it to terminate. Therefore, you have to say, I'm going to take the 10 elements of this infinite list. And then the computation will actually stop because I only wanted the first 10 elements. And then, the program will generate as much of the list necessary to generate 10 elements. But that's how laziness then is introduced, is the idea that it's a potential infinite, unbounded, but in practice, you're always going to bound it with some, number. But mathematically, when we define it, it seems like there is no problem with defining on infinite structures, right?
Well, I don't
Now,
know.
when it comes to trees, I agree with you. It seems like the depth of any leaf needs to be at finite depth. But the tree itself could be infinite, like an infinite list, right? So, because you could have, left is A, but then the right has two elements, two children, and one of them is a leaf, but the other one is not. Basically, representing an infinite list in a tree structure. But you could have, the at any leaf is finite depth, but the tree itself could grow and grow and grow. So a traverse defined on that, I think, could be done just like on a finite, on an infinite list as well. But I don't know if that would be helpful. I think the assumption that it's finite is good enough for most cases, right?
Well, the real assumption here is that it is a polynomial functor. Now, polynomial functor could be recursively defined, and then you can ask which fixed point you take. Do you take the largest fixed point, which includes all the infinite data structures, or do you take the least fixed point that only includes finite structures?
Right.
And I would say, yeah, well, if you write the code very carefully so that the result is also a lazy data structure that does not try to evaluate too much, maybe you can get like fold of an infinite list, which will terminate only if the updater is correct, and so on. If the updater at some point discards the element, and otherwise it will just not terminate. I mean, what if I say, I want to compute the sum of elements of the list, sum of all elements? That's a fold, right? With the updater function which adds numbers.
Right.
Right. Now I'm supposed to, well, this will never terminate in an infinite list. And then I say I have a certain function that will traverse, which will count how many times I traversed, and then I will stop at after 10 elements or something like this. Yeah, well then I mean I could imagine that working actually. But the thing is that you will then have a function that will sometimes not terminate.
Right.
Okay.
I agree with you.
I guess that's fine. I guess that's fine.
Yeah, I mean, this is a general kind of a issue with type theory and so forth, is that we want types to guarantee termination, right? Which is total functions. Yeah. But in reality, we often write functions that are not total. And so, to handle those, we need weaker, we need properties that are, and that's why I think Haskell, for example, introduces the lazy, right?
Yeah.
Semantics, because that allows then uniform treatment of the infinite structures in the same way as finite without distinguishing the two, except that as a programmer, you have to make sure that you're only taking finite number of elements and it will terminate. So the onus is on you to make sure it terminates, because the type theory is not going to guarantee that, right?
Right.
So,
Yeah.
yeah.
Yeah. Right. That's true. So I think in this book, I'm only trying to prove statements that don't depend on termination.
Right.
So I'm checking laws, for example. Now, if the functions terminate, they must satisfy the laws. If they don't terminate, I don't know. Actually, let me comment on the method of proof for recursive functions. So I use the same method throughout the book, which is that I go through the code of the recursive function, and whenever it calls itself, I put an overbar on that,
Mm.
and I say, well, this already satisfies the law I'm trying to prove.
Mm-hmm.
Right? So I can just go on with the proof, and whenever there's an overbar, the law is already satisfied in there. So what does it mean? It means I'm assuming that the recursive call terminates and gives me a value that satisfies the law.
Mm-hmm.
Right? So
Right.
if the recursive call does not terminate, then I won't have a proof in a sense. But if my function is lazy, so that this particular recursive call is not actually needed for the evaluation, right? Then it doesn't matter that it didn't terminate, and then I don't have to check if it satisfied the law.
Right.
So this proof is equally good in case I use laziness or not. But I do not want to go into that very much because I don't feel very knowledgeable about the theory of this. This seems to be very difficult. This whole laziness subject, and laws no longer hold unless you do a lot of carefully formulated conditions about laziness. I don't know. I've seen statements that monad laws no longer hold for the state monad because if this is lazy and this is not lazy and this is strict and this is bottom, then everything breaks. So anyway, so this is.
Now, you do use the example of a future.
Yeah.
And maybe you need to say something that you assume that all futures will return, right?
Yeah.
Because technically, some futures may not return. So,
Yes.
yeah, okay. So that's laziness kind of coming in.
Yeah, well, I mean, all I'm saying is that whenever I prove a law about a recursive function, I assume that all the recursive calls already satisfy this law.
Right.
So this is fine, and laziness may or may not be present, but as long as the function terminates in some way, with or without laziness, then the laws will hold after this proof. But of course, if the function does not terminate, we don't know what happens when it terminates or not. We don't know that.
Right.
So there are lazy. So even if you have no laziness in the language built in, you can simulate laziness using functions. Right. So you can have a function from unit to something, and that simulates laziness. And so, in principle, I have laziness also in my construction. So a lot of type classes allow non-polynomial functions, non-polynomial types, which includes laziness. So an infinite effectful list, for example, you have a value. The next value is not computed yet. If you want to compute it, first you have to evaluate some effect, run it, and then you get that next value. And the next value, again, contains the tail that is not yet evaluated. And if you want to evaluate, you have to run the effect. So at each step, you run the effect. So this kind of data structure is very general, and it can simulate infinite lists very easily.
Right. Right.
And
Yeah,
so,
that's what I meant by stream before.
yeah, it's an effectful stream where every next element needs to be found by first running some effect, and then extracting values, and then you only get one value, one next value. So then you have to repeat. And so this kind of thing is not traversable. But anyway, but ordinary list where you just silently take the greatest fixed point, right? You just write the definition of list, but you pretend that something is lazy somewhere. And that kind of thing would just fall through here. It will just some things will not terminate, and my proofs don't know about that. So I never provide for what happens when some functions do not terminate. So then this is a bit, maybe this is a bit simplistic, but I feel that this is the right level. Don't want to go into too much theory about what does it mean that something is terminating or not terminating. So anyway.
So we're done. Are we done with that? Yeah. I have a question about like this kind of phrase in Scala, because I think of monoid M. Now my not working. Monoid M as being a type whose instance would have an empty method.
Yeah.
But Scala so what's
no, Scala doesn't. It is not automatic. Now
so what is monoid M dot empty? What does that mean?
So I refer to standard implementations of monoid type class in libraries. It is not automatic, so maybe I should not have done it, and instead written some code that is more easy to read. So here's what you do. You have a monoid instance, which is implicit in this function. And then you define monoid companion object in Scala, which has a function called apply with type parameter M, and then it returns you the instance. So monoid of M returns you directly the instance of
by looking it up.
By looking it up. Now this in plain Scala, this would be written more verbosely. Let me write it down.
I forgot that. Okay, so monoid M is both a type and a companion object.
Right. Now this could be written like this, more verbosely, because you have to get the implicit argument over there.
I have a question then. I mean, now that Pete brought it up, now it's making me confused. But can't we just use M there? In fold map, left bracket M colon monoid, we're saying that M is a monoid.
Yes.
So couldn't we just say M dot empty?
No.
Which means the empty element of the monoid M?
No, because M is a type.
And M is a type.
Is a type parameter. It's a type, capital M is a type parameter, and it cannot have a companion object. There is no value capital M.
Then what is monoid square bracket M?
That is an companion object
type,
defined
but
in
also
the library.
A companion object.
That is defined. That is a standard way of reducing typing in Scala, but this is not very important. What we need here, we need to extract the instance for M, and from that instance, we need to extract the empty value, right? So how do we extract the instance? So this way is a standard way of extracting the instance if you have an implicit value in scope. I'm just reducing to have to type the word implicitly all the time.
Okay, I guess I was interpreting monoid m dot empty as the empty, the signature. I mean, the empty is the identity element for the monoid trait, right?
Yeah.
And therefore, any instance of any monoid has to have the empty operator defined, right?
Yeah.
And that's what I'm saying. Okay, so basically it's the same thing as saying implicitly we create a monoid and then we take the empty element.
Yeah, you could not
Because
write this.
don't you also need then something or surrounding the vertical bar plus vertical bar?
No.
Where does that come from?
So that's
Well, wait, so couldn't you just leave off the monoid M and just write empty here and it would work the same way this would?
no.
That's what I was thinking.
This you cannot do. This you
Okay.
cannot do because it doesn't know of which type the empty must be of which monoid. So because here this plus can be deduced by the compiler because the compiler knows that the type of lowercase m is the monoid type. So then it can find from the
Oh, I see.
context,
Okay.
it can find the operations. But the empty doesn't know where to look in which type this empty should be. So you could define a function like this, empty of m. You could define like this. And then at least you would know of which type to look it up. Because you could have different monoid types, right, in the same program. And so you have to, somewhere you have to specify the type. So you can specify it. So that actually maybe the most elegant would be to write like this, empty of m.
I guess, okay, but then shouldn't we type the m comma a on the when that anonymous function also? How do we know what m is here? The small lowercase m.
Well, a sequence has a fold left method, and the first element of that method, the first argument of that method, is
oh, I see. From the definition
value,
from the definition of fold left.
Yes. So the fold left has the first argument. It has the monoid type.
Okay.
And then the compiler says, okay, now I know the types of other arguments because it's the first one is a monoid type. The second one is this arbitrary type A, but that I don't care. I have F, so I can figure out that F of A is again a monoid type, and now I have a combination of two monoid types. So the Scala compiler can in certain instances it can figure this out. If you have a function, for example, you have some function of some type parameters, then the first argument is of type A, and the second argument is maybe of type B or whatever, right? And once you write the first argument, then Scala compiler will already understand that F capital A is fixed. So then it can figure out other things. If you don't do this, if you write it like this, XA and then Y something else, then it won't always figure it out because it's not a single element list. So at this point, this thing is a current function, and it determines already some types. When you write code like this, it's reducing the type annotations that you have to put in for Scala. So that's why actually all these library functions, they have the first argument, usually a very simple type to help the compiler. Anyway, this is just kind of Scala mechanics.
Yeah. Okay.
But yeah, so let me say that this I use it in different places in the book to, but I'm not sure I explain it well enough or at all. I don't remember now. This is a kind of a standard way that libraries like CATS define type classes so that you can more quickly get a type class instance.
Mm-hmm.
But yeah, this is certainly not, for this to work, for the plus here to work, you need imports already.
Mm-hmm.
It won't work without certain imports. And monoid needs imports. So a lot of imports are necessary to get this to work anyway. So if you have those imports, why not organize them so that you don't need to type so much? Anyway, that's what I wanted to
And
comment.
the imports are like from CATS?
Yeah.
Okay.
If you do like cats monoid.syntax, you import that, and then you get all the syntax things.
Okay.
And then you import cats monoid.data instances for standard types and all kinds of other things. What I found is that this is so little code to implement all these monoids and so on. It doesn't really warrant a library. Because you would spend more time learning how to use the library than implementing it yourself. And if you implement it yourself, at least you know what was going on there. And most of it is trivial. There are certain non-trivial things in CATS, certainly, but not the monoid stuff.
Mm-hmm.
If you just want to implement a little monoid somewhere, you can implement it in 3 lines of code and you're done.
Okay.
Yeah.
So a foldable is basically something that has fold map.
Yeah.
Is that right? Yeah.
Yeah.
And that's equivalent to fold left?
Yeah.
Okay.
And to reduce.
Mm.
And I have a different section where I show all that, why it is equivalent and so on.
Okay.
But first I want to show what we do with this and how this is used.
So that's what we're doing here, huh?
Right. Yeah.
Right. Just one thing, when I was reading this, kind of like you're going from an arbitrary monoid to an arbitrary applicative functor.
Yeah.
It's like,
Just compare
I'm still trying to wrap my head around applicative functors, and it's so clear with the monoid that you're basically you're doing this. You're just putting the monoid operation between these things. But
yes.
an applicative doesn't necessarily have. Does it necessarily imply an operation that it has an operation like that?
No,
Okay.
because applicative has FB going to F of pair BB, right? It's a zip operation. I mean, this is a zip operation, but there's no easy way of going from a pair of BB to a single B. If B were a monoid, then you would combine them, but B is not necessarily a monoid. It's arbitrary. And so the way to save things is that actually the result is going to be not FB, but F of L of B. You see, so if you look at the, compare the type signature of fold map and the type signature of traverse. And you see there's, instead of M, you have F of B. But on the right, you do not have F of B as a result of this. You have F of L of B.
Yeah.
Okay.
So it is not just that you replace monoid by arbitrary applicative functor. It is not straightforwardly replacing it.
Right. I mean, with the fold, you're doing a reduction on using the binary operator, but with
Yes.
traverse, you are keeping the original structure. That's where the
Exactly. Yeah.
LB. Yeah. Okay.
You have to keep the structure under F. So
Right.
under the wrapper, the original structure must be preserved. And actually, there's a law about that you have to do that. So if F, first of all, this must work in the same way for every F. And then you can take F to be identity functor if you want. And then you just have a function, that's just doing a simple map from A to B, from LA to LB. Right? So, and that should be that. So that's a law, actually, that we need to satisfy. And so this law kind of guarantees that you are preserving the structure under F. And that's the intention. So you need to preserve the structure under F.
Yeah. I think what might be instructive is in the definition that you have of trav, you go from L superscript A into F LB.
Yeah.
Maybe one sentence that says, if you apply the function A into F of B, you map that in LA, you would get L of FB, right?
No.
And then the tricky part of traverse then is that you are commuting those, right? So L of FB becomes F of LB.
Yeah.
And that
Right.
switching the L and the F, that's to me the critical insight into this. Otherwise, right?
Right.
But I think
that's how I remember the signature is that it's map inside out.
Right.
Map would be L of F of B as the result, as opposed to F of L of B.
No, I think I have a comment about this.
Okay.
Actually, look at this. Avoid errors, writing LFB instead of FLB. Yeah, okay. I think what you're saying is that I need to emphasize that this is not just map. This is not just map.
Right. Right.
Okay. Now, yeah, that makes sense. Yeah.
And sort of map would give you an L of F of B, and then that operation you were talking about before, sequence, that would turn it into an F of LB, right? So traverse is kind of like map and followed by sequence.
Right. Exactly.
Okay.
Yep. This is all explained later.
Okay.
Okay.
Just that the first kind of practical part, it tells you what you can do and how to implement those things. And then there's a more theoretical part that explores all those equivalences and relationships and so on. I mean, it's very similar to, for example, map and flatten that give rise to flat map. And so map and sequence gives rise to traverse. It's a very similar thing, and the equivalence is given by Yoneda again. So it's a very kind of, see, there's this equivalence where you have an arbitrary function from A to F of B, and then you map that, but you don't get what you want. You need another function to get what you want. Now, you can always say, well, let A be equal to F of B. The type A is arbitrary, right? So let's take A and F to equal F of B. And then the first function is just identity. And then you get just a simple function, which is sequence. So anyway, this is let's just go through the practical parts first. So here's how you implement traverse for a functor, which is 1 plus A times A.
Right.
Now, 1 plus A times A is a very simple but not very trivial functor. And now we need to preserve the structure. So we're trying to produce from option AA to F of option BB. So what do you do? Right.
Right.
So you can do applicative zip of the two values. And then,
Well, right. If it's none, then you just
Yeah.
return pure none.
That's right.
Right.
You
So you're
preserve the
just
structure.
pushing
Yeah.
none into
Yeah.
F.
Right.
Okay.
Right.
But
And then
otherwise, yeah, you zip it.
right. And then you zip it, and then you have to preserve the structure. So you still put a, you have an option of BB under F. You need to create that. See,
Right.
after the zip, you would get F of BB, not of F of option BB. So you need to put the, then you have a last map, which is
Right.
just putting the option on top of it.
So you have this pair, and you
Yes.
tear the pair apart, and then sort of put it back together with a
That's
wrapping
right.
it in a
That's
sum.
right. Yes, that's right. And so the result is that we preserve the entire structure of L under F. So if L were empty, then we have F of empty, F of none. And if L were a pair, then we have F of some pair. So, and the effect of F has been combined by the zip. Whatever that effect is, we have combined those effects. So we just use,
And that's the key, right? That's
yeah.
because like with the monoid case, you have the monoid operation to kind of
Yeah.
put things together. Here,
Yes.
the equivalent thing is this zip. Well,
Right.
zip and map together, I guess. But
Yes, yes. So you have to do that kind of combination, yeah.
I see. I see.
And yeah, I mean, this is essentially, you can also say this is map 2, maybe in some way.
Yeah, I
but,
was wondering about that.
but
Kind of
to
like
me,
zip with.
yes,
I've heard that, but map 2, I guess, is what that is.
Yeah, but this is kind of cleaner just to think about. So you do a zip, and you have that, and after zip, you have a map.
Put it back together. Yeah.
Yes. So then, yeah. So then I say, well, this is what needs to be done. The code works in the same way for all applicative functors because it just uses the methods of the applicative functor, regardless of what that is. So,
Okay. Yeah.
and the same thing you do in
List.
in list. Yeah.
Right. If it's nil, push the nil into F, and otherwise.
Right. Then you have a recursive call.
Right.
Right, to get the tail, and then you put the tail back in.
Right. So zip will take these two things and put them as a pair inside F, and then
Right.
this
Yeah.
takes them out and makes it into a list again. So yeah.
Right. Yes.
And binary tree.
Right. Now the binary tree needs to reproduce the structure. So you do a zip and then map to make branch or to make leaf. So under F, it's the same structure as before.
Yeah.
Mm-hmm.
Right. This is the easiest reversal. It's the depth first, which is easiest to write for the tree.
Yeah. Right. And then for the P tree, that's kind of interesting because it's actually sort of not a tree. It's actually a straight line thing, but the stuff inside is getting bigger.
Yes. I mean,
So Here,
zip.
the zip is inside this
Mhm.
function
Yes.
instead of being outside and then putting it back together. Here, it's like you're getting the pieces, but you have to zip them inside
Yes.
before you put them together. Something like that.
Yes. Well, this is a little hairy, but it's again it's guided by the same idea that you want to preserve the structure of your data type under the wrapping. So you do the zip so that you wrap everything under F, but then you have to do all this map at the end to preserve the structure. Now, what exactly is the traversal order here? So we traverse kind of top to bottom and left to right. Because the zip inside that you talk about, this zips the pairs, right? Because the F, so this is because you have now a pair of AA and a pair of BB, and so now you have a
You're
pair
trying
of
to
AA,
produce a pair
yeah.
of BB, right?
and now you need to produce a pair of BB, which means that you are concatenating the effects together of these AA next to each other. So your traversal order is really that the pair of AA is traversed next to each other, always. So because you're concatenating the effects of F in that order.
Right.
So
And that's important because zip is not commutative or anything
no,
like that.
no,
In fact,
no.
it's very much left to right because you're kind of pushing the effects in that
Oh,
direction.
in some
Or-
cases it can be commutative. It's,
Can be, but not necessarily.
right. So this is the basic idea of how to implement the traverse operation. So then I make a comment that this is kind of general. So you have a container-like data structure, which is some kind of functor that has a bunch of values inside. And you just choose a traversal order, merge all the effects of F using zip, and then use map to reproduce the shape inside. So because after zip, you won't have a shape. You'll just have some pairs, some tuples after zip. That's not good enough. You have to reproduce every bit of shape information. So if you have a branch or a leaf or some other thing, and you have to put it in there.
Mhm.
And so
That's what the map part does.
Yeah. Yes. So that is the point of traverse. So traverse needs to do quite a bit more work than fold. And that's why you cannot just take fold and convert it into traverse. Traverse needs to do more work. But you can do back, go from traverse to fold. You can discard all this extra information. That's easy.
Mhm. Okay.
Yeah. Then I give an example of a bad traverse that collects effects twice.
Right. You do F of head, zip F of head,
Yeah. And then
blah, blah, blah. But then you have to throw one out.
yeah, I just throw one out. Yeah. Now this is strange. Why would you do that? Right. And this is not what you expect traverse to do. It's not supposed to do that. Some laws are necessary in order to prohibit this kind of implementation.
And we'll get to that later.
Yeah, so this is just a motivation to say that this is not so clear, and we need some more laws to fix that. Yeah. Right.
Maybe before we go on to this section, it's like 7 minutes out. Should we pick our next meeting?
We can certainly do that. I was just looking at the calendar, and at the 2 weeks from now, I will be probably standing in a security line at San Francisco Airport for our flight to London. So that's probably not good for me.
Don't have Wi-Fi there, huh?
Oh, the
Well-
security line could get longer.
The security line could be long, and I'm not sure that they want you to have your laptops out, but I'm not sure they want you to be actually interacting with your laptop while you're in the line. So, and then the week after that, we're in Amsterdam and hanging out with my friends. They probably wouldn't appreciate the interruption. So, you guys could meet without me, or we could wait until the 30th, which I think we have no conflict on.
30th of September.
30th, right,
Well, it's fine
4
with
weeks
me.
from today. Is that,
Good.
Yeah,
Good.
that's
Well,
okay.
I guess, you need, it's a heavy chapter. Why don't you implement some traversals and so on?
Right.
Or maybe find some, the reason why you can have a traversal on a lazy list.
Right.
Yeah.
And maybe we'll sort of plan to get into the laws and structure part too.
Yeah, well, I
In
have quite a
4
bit
weeks.
of stuff. Yes, well, I have quite a bit of stuff here on the recursion schemes and traversal of trees and so on. So
Oh yeah, right.
right,
um,
and
That's pretty heavy too.
it is,
so let's try to get through that.
Okay.
yes. It will make wonderful vacation reading. So, all right,
You got airplane flights.
yes,
Right. Take care.
okay,
All right, thank you.
all right, so see you all in 4 weeks.
See.
All right.
And,
Okay.
Take care.
yeah, and we'll pick up
Thanks,
from
Sergey.
So,
section 12.2, or however far we've gotten into it.
Right.
All right, bye.
Bye.
Okay, till then, bye.
All right. See you.